Okay, so here we have another example in class 22, and the last video, for whatever reason, turned out like really small. I don't know what happened there, but it's a mystery. Here's problems 617 and 654, I think, or they're related to it. So we have this shaft. It's only two-dimensional. And we have these forces F1 and F2. There's 2,500 and 1,000 pounds that are applied to this shaft. It's rotating. Yes, it's rotating. And it has a load, a steady torque of 2,500 pounds inches. And we want to know how much horsepower is transmitted. It's a good thing to start. And we want to determine the minimum fatigue factor of safety based on achieving infinite life. And if it's not infinite, we want to estimate the number of cycles. And we've done a little bit of preliminary stuff right here. It appears to me as if we've already decided to use the 1 5/8 location, but a lot of times we'll actually have to look for where the worst case scenario is going to be. But I guess we've already decided that it's going to be right there. But anyway, we already have the endurance strength, the fully corrected endurance strength, and we have A and B. So a lot of stuff's already been done for us. So let's go in here. All right, so the first thing I asked is how much power is transmitted. Well, they told us the RPM, right? Yeah, 1,600 RPM and the steady torque. So we can find the power by taking the torque times the RPM divided by 63,025, which is an equation 342 in the book if you're looking for that. And so that goes 2,500. That should be the RPM, right? No, that's the torque. Yeah, that's the torque. Shh. I got it right this time. Okay. 6325, and we find that 63.5 horsepower. That's always a good thing to do, to try to kind of maybe like think about something that you know is in that range. You know, this is more than my riding lawnmower. It's less than a very small car. Less than most small motorcycles. So I think that I had a 75. I don't know. You get kind of an idea of what range it's in. So anyway, let's see. We're going to start off with our statics. Always want to start off with our statics. And so I'm going to draw the thing with a little bit of detail because I want to zoom in on the important stuff right here. Right? So it's got that change in diameter because it's a stepped shaft, and another change in diameter right here. And even another change in diameter right here. I guess these are actually kind of small right there, right? So, oops. I should have made this maybe a little bigger, but whatever. All right. So what we're trying to do as we come through and work on problems is to get them closer and closer to real, quote-unquote, real life. Quote-unquote real life. Why did he say it that way? I don't know. It's weird. Okay, so the reactions are going to be here and here at the center of the bearings, right? And this one was 2,500, 2,500 pounds, and this was 1,000 pounds. And this was A, so this is going to be R-A-Y. And this was B, I guess, so R-B-Y. All right, so we didn't label any of those other points right in there. So we want to get, we could actually get this location, but we don't really need it right here. We kind of know that that's, the moment's not going to be really large right in there. But there's a torque in between these two right in there, so we want to get a hold of those. So the sum of the moments about A is equal to 0. So let's see the distances that we're talking about. This is like 8 inches in between here. There's 8 inches in between there. That makes it life easier right here. And this is 8 inches, even though I didn't draw it. so that it looked that way. Okay. So let's see. We're going to have, let's go clockwise. 2,500 times 8. Okay, this is negative, right? And so this would be negative 1,000 times now 16, right? But this is positive RBY times 24 equal to 0. All right, and of course you are all really good at this by this point. So RBY, I'm just going to go ahead and write down what the actual number is. I think it's 2,000. 2,000 pounds, sum of the forces in the y direction. So we get RAY and minus 2,500 and minus 1,000 and then plus 2,000, because that's that guy. And we get RAY is equal to, where are you, RAY? It should be 1,500, right? 1,500? Sure. And so, coming through here, we come across and have 2,000. Then we're going to dip down and go to negative 500. And that's the same thing true all the way there. And then we're going to dip down another 1,000. So here's a negative 500. And here's a negative 1,000. This, of course, is V, and these are in pounds. So when we get to our moments right here, we will find, we'll get to here's 2,000 times 8. So here's our moments. And that is 10,000, right? So 10,000 inch pounds. And then we're going to drop down to right here. So we're going to go 500, negative 500 times 8 plus that right there ends up getting, we can go the other direction too, can't we? Well, this is supposed to be 1,500. I don't know why the hell I wrote 1,000. 1,000, negative 1,500. Silly. Anyway, let's see. I believe that comes out to 12,000. But we're also going to want to know this point right there because we're interested in that location. So that comes out to 17. No. It comes out to, I just did this wrong again. How did I manage to do that wrong? Oh, I'm just not with it today. This is 16,000. And that looks like it's 14,750. There you go. I think I got the numbers right now, right? So this right here is where we're going to want to concentrate because there's a stress concentration right in there. So we could look at some more paper here. Okay. So that stress concentration, what did I decide to do? Oh, I looked up and I saw that my ratio, my big D over little d ratio, was, coming back to the original problem right here, we went from big D, focus, 1 7/8 to 1 5/8, and all the fillets were 1/16, right? So let's come back up here and say big D over little d is 1.875 over 1.625, which gives us like 1.15, or pretty close to it. And then our R over D is going to be 0.0625, that's 1/16, and 1.625, and we get 0.03. I said 8, but I think it's 375 personally, but I didn't put any more sig figs in there. And I said that my KT for bending was approximately 2.0, and my KT for shear of torsion was 1.6. My Q, based on the ultimate strength, which we was 85, right? And the 0.0625 the 1/16th, I get 0.765, right? So if we apply those together, we end up with a KF of 1.77. I didn't bother with more sig figs, but I don't know why. The shear, 0.812, either from the graph or from the equation. And combining these two together, we get a fatigue stress concentration of 1.49. You can look up in previous videos or whatever to see how we got from these two things into there with the equation. I'll write it down. KF is equal to 1 plus Q KT minus 1, right? Right there. So that's how we got those two. All right, good. Okay, and now so we want to get the nominal stress. So the nominal bending stress is going to be MC over I. And I didn't bother calculating the I. So we could also go, if we wanted to, 32 M over pi d cubed if we wanted to. Either way. But we're going to use that 14,750 pi, and the diameter is 1.625. That's right, he is, right? Yeah, third. And then I'm going to divide by 1,000, right? So just I'm going to write it down. I'm going to divide by 1,000 in my head to get that 35 KSI. 35.01 KSI, actually. Okay. And then the tau nominal, and go 16 torque over pi d cubed if you wanted to. 16, and the torque, they gave it to us, right? 2,500. Pi 1.625 cubed. And what do we look? 2.967, so not nearly as much torsion as this. All right, so now we want to get the alternating and mid-range von Mises stress. All right, so for the alternating, it's kind of like, I'm going to write out the equation, but then we're going to see that's not necessary, right? So you're going to have KF times sigma A squared plus 3 times KFS tau A squared 1/2. But it's got a steady torque. So the only thing we got going on here is the square root of the square of KF times. So this is really just KF times the alternating, which is this guy right here, right? So this is the only thing. This is alternating, and this is steady. Therefore, this is a mid-range, and this is an alternating, and the only thing we're doing is just to multiplying that KF right there, the 1.77 times the 35.01. So we're left with 61.79 KSI. And then for the mid-range, right, all those same things, KF alternating mid-range normal stress 3 times KFS tau mid-range squared 1/2. But the mid-range is 0 because it's going back and forth between tension and compression. So the mid-range is 0. It's always, that's like, halfway in between the maximum and minimum. 0, right? But this one's still, so what we still have to be careful because we still have that 3 in there, right? And so we could actually simplify this and say the square root of 3 times KFS times tau mid-range. I'll call it nominal right here, but that's what we mean right here. That guy is the same as that one. So square root of 3. I didn't draw that very well. Let's try it again. Square root of 3, 1.49 and 2.967. and that comes out to be 7.644. So still not nearly as important to us as the alternating. So there's a lot more alternating going on right there. So anyway, let's do the Langer to check for our first cycle fatigue, which is going to be the yield strength divided by the alternating and the mid-range added together. And so that's 71 divided by 60.79. What the hell did I have one there for? And then 7.644. And we find this is 1.02, so it barely passes. But we mostly want to just estimate the life of the thing. So you see we go to Goodman, which is 1 over alternating over SE plus mid-range over S ultimate. And I'll put the numbers in there. Why not? 61.79 over 29.5, which we were essentially given, and 7.6. Is that a 9.4? I can't tell. It looks like a 4.4. I think it is. And the ultimate was 85, right? So we get 0.46, and we're not finite. Therefore, we want to get the completely reversible equivalent stress, and that's going to be the alternating divided by 1 minus the mid-range divided by the ultimate. So 61.79, and this is not really going to be a big difference because of this. So the thing, because this is so small right here, and we get 67.90. So we're going to plug that in to our N is equal to the reversible divided by A raised to the 1 over B. And we were given these two values right here. We can find them ourselves if we wanted to. And so we take a 67.9 divided by the 184.1 we were given in the previous page. 1 over the negative 0.1325 we were also given in the previous page. We got 1,900 cycles. So we're almost in low cycle fatigue. Anything below 1,000 is on that other leg of the SN diagram, right? That SN diagram, remember, goes 1,000 and then 1 million right here. And right here is ultimate. Right here is FSUT, and then down here is the endurance strength, and we're really only calculating for this range is when we can do this, but we just plugged up a stress that apparently was like really close to that 1,000, or pretty close to that 1,000, right? So because we got 1,900 here, but we were also given the RPM, right? So that's really actually so close. So the time is approximately like 1.2 minutes, or I think even at 1.15. But we don't want to. You don't get your stopwatch out and say watch the thing break, right? Because this is not that kind of calculation, right? We don't know. We don't have a high degree of confidence that this and probability that this is actually going to happen. We were like 50% reliability, which isn't good. But it's heavily loaded. All right, so in the next class we're going to do more design stuff. So hopefully, hopefully this the aspect ratio of this video isn't going to be weird like the last one. I don't know what happened there.